Welcome to the Intro to Quantum Information and Computation project. We're presenting the topic physical implementation of quantum computers, and our group number is 10. Before we start, we'd like to extend our boundless gratitude towards the director, Dr. Srija Narra, and the respectful dean, Dr. Kishore Kottapalli, and our IQIC professor, Dr. Indranil Chakraborty, and our TA, Mr. Suryan Srivastava, and everyone who has helped us at IIIT with the expertise and environment to uh, make this project. So, with that being said, let's dive into the project. And our team members are Siddik Ayyappa, me, Anurag Gupta, Srija Narra, Aditya Kumar, Seetha Raghavendra. And we are going through these contents in this project. So in the beginning, we're going to get started with quantum computers with a little intro of what they are, and then we're going to look at various implementations of them, especially qubits, since qubits are of the most importance. And at the end, we're going to look at hardware and some sturdy stuff. So we have all been hearing the word quantum all around. So it's certainly been hyped a lot. Adding the phrase quantum to something would hype it a lot. So would that be true with computers? Definitely. In fact, it's the most truest thing with computers. Um, well, why? We shall look at it. What makes quantum computers so powerful? We all know that bit is the fundamental building block of a classical computer, whereas qubit is the fundamental building of a quantum computers. Now this is where the difference in the efficiency occurs. Bits are like switch states, they can either be 0 or 1, whereas qubits, something called superposition and entanglement, get into the picture. And this is where things get interesting. They can simultaneously be either 0 or 1. I'm pretty sure this is a hard thing to wrap your head around, so I'm gonna give an analogy like reading a book in a different way. So let's look at the analogy. Imagine you're reading a book. We usually read from page 0 to page n. That's serially reading. So this is how classical computer does stuff. Let us imagine by some phenomena we are able to scramble the pages, all the pages. So every page is a superposition of all the pages, and we are somehow able to read all the pages at once. And with that, we are descrambling the content we have read and then taking in information. So let us say the time taken to read a page is n and the number of pages are m. If we read it serially, it takes mn time. If we do it in the scrambling way, it just takes n. No, doesn't matter. It doesn't really matter how many pages we have, and so as long as we have the method to read all the m pages simultaneously. This is the basic idea of quantum computers.
This is the implementation of the photonic qubit. A basic overview. Various physical entities can be used as a qubits. For example, we can use ion traps, superconducting charges, and many more. These are also the things we can use as a qubits in the quantum computing. And what makes the photonic qubit unique over the others? Yes, photonic qubit has some advantages and some difficulties while implementing to the others compared above. The main advantage of the photonic qubit is its thermal noise is low. It doesn't need extremely low temperatures to operate, which can be quite useful since most of the CPUs are just needed very much a low temperature to give the best performances. And the main difficulty of the photons is that they do not interact with each other. uh, this is the one of the major difficulty. This will be a huge problem while implementing the 2 qubit gates. In this we will discuss some of the 2 qubit gates and single qubit gates implementation. Next, how the photons are represented as a qubits. There are two ways we can represent a photon as a qubit. First one is dual rail qubits. Since photons travel in a straight line, we can select two paths. If photon travels in the one of the path, we can name it as 0. If travels in another path, we can name it as 1. The both representations are given here. And the next one is polarization qubit. Like every photon has degrees of freedom, and in which they carry the information. We take H and V as the horizontal and vertical polarization. These are the two ways in which photons are represented as a qubits. Um, Next is single qubit unitary operators. In this, the first one is the phase shifter. The phase shifter is, if we take a slab of the variable refracting index. If we pass it, then if there is a phase shift of 5, then we can say it as a n is equals to a out into ei5 into a n, which can be used. And next is the beam splitter. In this beam splitter, we send the two waves as a in and b in to the slab. To the slab. The outward equations are a out and b out. And there will be some reflections, and these are the ones we are finally getting, a out and b out, which is represented as cos theta, and this equation a out, and b out is this equation. uh, uh, with the help of beam splitters and phase shifters, we can represent we can induce any rotation in the qubit in the blast sphere. Like it's theta and phi, we can change its course to a single plane in this, and we can rotate it by using phase shifter, so that it will cover whole the sphere. We can change the photon in an we can change the qubit in any angle. It is possible. Next is polarizing beam splitter. This beam splitter is mainly used to separate H and V components. In this polarizing beam splitter, it splits the path of the incoming photon with respect to its polarization. If the horizontal paths will come without any reflection, the vertical path uh, will go exactly perpendicular. It will reflect. If you want to convert a dual rail qubit into the polarizing qubit, we can induce polarizing beam splitter in it, uh, and it will take the action. Next is earlier attempts to implement 2 qubit gates. As we discussed in the starting, qubits, photons are non-interactive in nature. Thus, due to that, implementation of qubits is a tough thing. The first one is done by Sir Fardam and White. They have implemented a CNOT gate using linear optic elements with a combination of beam splitters and the phase shifters. This implementation was not scalable, since uh, uh, when there is an increasing in the number of qubits, the resources needed are exponentially large. So that this is nonlinear quantum computers. In this they used Kern nonlinear material whose properties depend on the number of photons passing. This implementation failed, since they are the objects they have used, they are not getting as high amount of phase shift as required. We require the phase shift of about 5, but the phase shift is in the magnitude of 10 power minus 18, so it's not scalable. The next one is KLM protocol, implementation of 2-bit gates. The first one we discuss here is Hall-Mandela effect. This is the effect we will see uh, when two photons simultaneously reach two parts of the 50-50 beam splitter. It will show us as C5. Here theta is the is the A out. Here d tau is the B out. This can be represented as this. With this they came up they came up that we can use we can use this effect and create the NS gate. From that NS gate we can use to create CZ gate. And first one is NS gate. In the NS gate they have used three beam splitters, one phase shifter, and this is the setup they have put, and these are the three shifters, and these are the values they have given. While doing this, the only success probability for the NS gate is 1/4, which is quite low, since if you take four tests, only one of them is passing. And then they have implemented CZ gate with using two NS gates, and the success rate for this still falls, since the success rate of one NS gate is 1/4, and second NS gate is 1/4, total 1/16, which is very quite low for the CZ gate, since we will use exponentially large number of CZ gates in the large scale implementation. So this is also not not suitable, but in the further research they have improved the CZ gate by using quantum teleportation fix and all. So the conclusion, photonic qubits have it offer a range of advantages or other form of quantum computers. Main problem is that non-interacting nature of photons, which delayed the huge progress in development. Since the publication of KLM protocol, a lot of development process to the photonic qubits, such as implementing of Shor's algorithm, etc. That's
the implementation of superconducting qubits. To understand anything about quantum computers, the first thing we need to understand is the two most important phenomena in quantum mechanics. First, quantum superposition, and second, quantum entanglement. Quantum superposition, it's a phenomena in which a system can be in two states or a combination of two states at the same time. Example, a qubit can be used to represent 2 to the power 64 values at the same time. Quantum entanglement is a phenomena that states that two entangled particles know about the state of each other even when they are a large distance apart, and their behavior represents so. Example, if the spin of an electron in an orbital is reversed, the other electron of the orbital will have its spin automatically reversed even if they are kept on two separate ends of the earth. Now that we know this, we'll start building a superconducting quantum computer from the classical computer. The two computers, classical computer and quantum computer, differ in two major aspects: the way information is stored and the way information is processed. In a classical computer, we use bits that store information as zeros and ones, and we use a DRAM circuit to store the information. The transistor that stores a bit as 1 uses around 300,000 electrons to store that information. We could have just used 1 or 2 electrons, but these make the system susceptible to leakage and loss of information. So we come to the topic of quantum bits. Quantum bits or qubits are primary information storage mechanism in quantum computers. They use the previously described quantum phenomena, quantum superposition and quantum entanglement to store the information. Let's see how. We use the states of electrons to store the required information. The spin state and the energy level of the electron determine the value of the bit they are supposed to store. We'll see more on how superconducting qubits use this and how they are built. Let's start by applying the principle of superposition and entanglement on classical bits. It wouldn't last long. As soon as we do the first check against a DRAM error, we have forced the bit into either 0 or 1, removing the quantum superposition state. As long as the system remains unobserved, the system maintains a quantum state, but when there's an interaction or there's an observation, the system breaks. It splits, it acquires a classical state. It is either 0 or 1. It does no longer maintain the quantum superposition. In fact, the collapse happens even without us checking for errors. A single photon interacting with just one of our electrons can carry off the information. When this happens, it is as if the photon observed the quantum state and the state collapses. This is as if the nature was observing and destroying our quantum state. So, what do we suggest we do? In a case, we can increase the number of electrons for each bit. This increases redundancy and increases the chance of loss of information to unintentional observation, causing collapse of quantum states. In one case, we can even reduce the number of electrons for each bit. This would make the system more susceptible to physical noise and increase chances of quantum errors. In superconducting qubits, we use the best of both worlds. Certain metals, when cooled down below a threshold, start behaving like superconductors. Electrons bond to form a single unit, and the individual electrons are no longer scatter, reducing quantum errors to almost zero. We have seen how quantum and classical bits vary in the methods of data storage, and now we see how they vary in the mechanism of performing computation. In classical computers, data is retrieved from RAM, sent to CPU for processing, and then placed back into RAM. This much movement of data is not safe in quantum computers, and so we make a grid of interconnected qubits. Qubits stay put, and we send control signals to qubits to perform the computation. Now we see how superconducting qubit look like in reality. It is made using a capacitor that is made of superconducting materials like niobium and aluminium. To maintain the quantum phenomena, the qubit is stored at a temperature less than 15 millikelvin, so that thermal energy does not become a cause for loss of data to noise. A distinct feature of superconducting qubit is a Josephson junction. It is explained in the later slides. Quantum gates are the basic operations that are performed on the quantum bits to make basic computations. Let's single qubit gates. An arbitrary single qubit gate is achieved by a rotation in the Bloch sphere. The rotations between the different energy levels of a single qubit are induced by microwave pulses sent out to an antenna or a transmission line coupled to the qubit, with a frequency resonant with the energy separation between the levels. Individual qubit may be addressed by a dedicated transmission line or by shared one of the other qubits of resonance. The axis of rotation is set by quadrature amplitude modulation of the microwave pulse, while pulse length determines the angle of rotation. In the equations, the first equation shows the driving signal of frequency omega d. A driven qubit Hamiltonian in a rotating wave approximation is given by the second equation, where omega is the qubit resonance frequency and sigma x and sigma y are Pauli matrices. Coupling qubits. It is essential for implementing two qubit gates. It can be achieved in two ways: connecting qubits to an intermediate electrical coupling circuit, for example, a capacitor. Decoupling the qubits is achieved by tunneling the qubits out of resonance one from another, that is, making energy gaps between their computational states different. This approach is inherently limited to allow nearest neighbor coupling only, as a physical electrical circuit has to be laid out between the connected qubits. The second method that we can use is coupling qubits to an intermediate bus. It is implemented as a microwave cavity modeled by a quantum harmonic oscillator. Coupled qubits may be brought in and out of resonance with the bus and with one another, hence eliminating the nearest neighbor limitation. The formalism used to describe the coupling is cavity quantum electrodynamics, where qubits are analogous to atoms interacting with optical photon cavity. Now we come to two-qubit gate. Cross-resonant gate is an implementation of a two-qubit gate. It includes two qubits and a bus, all tuned to different energy level separations. Applying microwave excitation to first qubit with a frequency resonant with second qubit causes a sigma x rotation of the second qubit. The rotation depends on the state of the first qubit, allowing a controlled phase gate construction. The drive Hamiltonian describing the system excited through the first qubit driving line is given in the equation that follows, where at is the shape of the microwave pulse in time. Sigma 2 bar is the resonance frequency of the second qubit. I, sigma x, sigma y, and sigma z are Pauli matrices. J is coupling coefficient between two qubits via the resonator. Delta 1 2 is omega 1 minus omega 2, that is the qubit detuning. M12 is the unwanted coupling between the qubits, and h bar is h by 2 pi, where h is the Planck's constant. Now we come to the Josephson junction. A distinct feature of the superconducting qubit is a Josephson junction. It is an electrical element that has a weak connection between two leads of a superconducting wire. The current flow through the junction occurs by a mechanism of quantum tunneling. More details about Josephson junction are present in the slide, which can be read out. So what are the challenges in the implementation of superconducting qubits? Theoretically and computationally, we don't face much challenges when there's an implementation of superconducting qubits. But there come physical constraints to the implementation of superconducting qubits, that are material defects. Since we need to, when reading out a qubit, it is a very magnetic field and electrical field extensive process. The electric field of the metal pushes down on atoms that may cause certain loss of energy or change in state of the electrons. Atoms in general vibrate at a certain frequency. Atoms wiggle, sending off waves that might cause the change in states. Information leaks happen due to noise factors. For instance, information leaks happen due to physical noise factors such as thermal energy. If the temperature of the surroundings goes a little bit above board the required, all the information might get immediately lost due to thermal noise. That superconducting qubits come with their own pros and cons. They are easy to understand and build, but extremely difficult to implement due to the necessary physical conditions like availability of required metals and achieving extremely low temperatures. Thank you.
Hello, my name is Aditya Kumar and I am from Team 10 IQIC project, and my topic is trapped ion qubits. So let's start. What are trapped ions? An ion trap is a combination of electric or magnetic field used to capture charged particles, which we know as ions, oftentimes in a system isolated from an external environment. This means that we use electric or magnetic field or a combination of electric and magnetic field to capture charged particles called ions, generally in times where they're isolated from external conditions. How is this useful in quantum computing? We use this concept to develop quantum computers. Okay, so let's see how. Before going into that, we are discussing some pros and cons of using trapped ion qubits. Some of the advantages of using trapped ion qubits is the long coherence time. Coherence time is nothing but basically the time in which a quantum qubit can independently exist in a given state. So the more the time, the better it is. The more, if the coherence time is more, the quantum qubit can survive for a longer duration of the time. That's why the coherence time is very necessary and should be increased while making a quantum computer. Basic gates which we develop using the trap ion mechanism is somewhat faster than neutral atoms. This is a basic, very nice advantage that we get while we use trapped ion qubits. Individual addressing straightforward. Using trapped ion qubits, we can use individual addressing. That's a very important factor. High precision experiments already commonplace. This is just the laboratory work done in the recent year. High precision experiments means that we can improve the computation power is very high, such as in optical clocks and various other instruments. Okay, some disadvantages are scaling to many qubits shall requires many ion traps. That is a big disadvantage because a lot of ion trap requires a lot of cost, a lot of time, and a lot of reduction in efficiency also. Slower gates than many solid state implementations. Some of the gates are faster than neutral atoms, but much slower than solid state implementation. That's a disadvantage, but rest it is fine. So let's see how trapped ion quantum computer works. A trapped ion quantum computer is one proposed approach to large-scale quantum computer. It can be built in a large scale. This means ions or charged atomic particles can be confined and suspended in free space using electromagnetic fields. That is just telling how ions and trapped ions are used. Qubits are stored in stable electronic states of each ion. So ions have different states as per their bands, valence bands. So electronic qubits are stored in each stable state, electronic states of each ion, and quantum information can be traversed through the collective quantized motion of the ions in a shared trap, interacting through Coulomb force. So this is just saying like we interact these mm, two ions and we get some information out of them. So that's how information can be transferred. That's a method of transferring information. And it says laser are applied to induce coupling between the qubit state for single qubit operators. Lasers or coupling between the internal qubit state and the external motional state for entanglement between qubits. This says how can we generate different states, right? Induce coupling between the qubit states. So this says how can we generate different qubit and different phase states using a trapped ion. Lasers are very useful for that. The fundamental operation of a quantum computer have been demonstrated experimentally within the current higher accuracy in the trapped ion system. This means that this method is the far more the best method that has been very promising towards the development of quantum computers in the modern era. Promising scheme in development to scale the system to arbitrarily large number of qubits, including transporting ions to spatially distant location in an array of ion traps. This means that we can really transport. Just talking about how quantum transportation of ions works in an array of ion traps, building large entangled states. This means the more the ion traps, the more larger the state vector will be, so the more complexity of the information will increase. Building a large entangled state via photonically connected networks or remotely entangled ion chain and combination of these two ideas. This makes trapped ion computer system one of the most promising architecture for a scalable universal quantum computer. So let's now see what has been developed in the laboratory right now. So till now we got a 250 ions per qubits. That means the number of ion traps per qubits. High fidelity quantum gates. This shows that how well the ion trap has worked. We have also generated some simple quantum algorithms that work with the ion trapped quantum computer. Teleportation is a thing which we have done, but we have accomplished only within a ion trap. Error correction. Okay. Some sort of error correction and quantum simulation algorithms. Some example of ion trap is Paul ion trap. There are more than this Paul ion trap. There is called another one Penning ion trap and Kingdom trap and Orbit trap. But for now we have just kept our project till Paul ion trap because it's the most generally one that is used. Thank you.
Now, this part tells us about the hardware related information in quantum computers. A prerequisite before we look at things. Some rules, no big deal. Rule number one, qubits shall be represented in Dirac notation. For instance, consider Cat1. It's a two column matrix, and that is a single qubit, and the rest of the rules are self explanatory. Now, just like we have NOT and OR gates in classical bits with which we can manipulate them, in quantum mechanics we have quantum gates. The following page shows us the gates and the manipulation they do to the qubits. Remember, qubit is not a number. It's a two column matrix and the gate is a square matrix, 2 cross 2 1. The qubit is multiplied to the matrix and we shall get another two column matrix, and that is another qubit. For example, consider the Pauli X gate. It is used to invert the qubit. So If you use Pauli X on ket 0, it shall become ket 1, and if you use it on ket 1, it shall become ket 0. The following image consists of the manipulations and matrices of the quantum gates. Now, I can hear a question. We all know that NAND and NOR gates are the universal gates in classical bits. What about universal quantum gates? There are various number of ways to do it, but the most used one is C0 gate, H gate, S gate, and T gate. Quantum reversible gates are special. By looking at the output, we can predict the input. Um, for instance, consider the NOT gate in classical computers. If the output is 0, it means the input is 1, and vice versa. Now, this reversible gates help us in reversing the sequence, which means they are useful in finding the inverse functions of the sequence of gates, which is quite useful in most of the scenarios. Now, hardware. We all know the von Neumann architecture of the classical computer. The figure on the left shall explain it. Now, for a quantum computer, the figure on the right shall explain the architecture. There are various ways of implementing qubits as we have seen in previous cases. A bit is viewed as a charge on the capacitor in a quantum computer, and just like that, a qubit is viewed as some sort of, I wouldn't say sort of, a quantum property of a particle. Depends on the implementation. For instance, consider the topological bit qubit implementation. We look at the spin of a Majorana fermion as the state. Now, all of the implementations, well, most of them have something in common: microwaves. They're all passed through microwaves and magnetic fields for getting the superposition and entanglement. Now, just like a classical computer has CPU, RAM, control unit, and the registers, a quantum computer has a QPU, a quantum processing unit, QCU, a quantum control unit, Q registers, QRAM, quantum random access memory, and a classical computer with an interface with the quantum computer we're making. The classical computer is called the host computer, and it is used to view the data we are getting out from the quantum computer. Now, since it has an interface with the quantum computer, we can modify the operating system of the classical computer to work efficiently with the interface of the quantum computer. And this is because the data would be received in a whole new format. And saying that, we can conclude the hardware module. We have come to the last section of the presentation. Let us learn about topological qubits. For starters, what are topological qubits? We know that maintaining a quantum computer is just as hard as making it. Why? Because they are so susceptible to the environmental disturbances. First, topological insulators. They are insulators on the inside and conductors on the outside. Now, this is our ticket for making stable quantum computers. The topological insulators available right now are shown in the slides. When two topological insulators, the same ones, interact with some phenomena, they emit a particle called as Majorana fermion. The unique quantum numbers of this particle is what makes it interesting. Since we added the topic in a physical implementation project, you may ask, why? Well, you just call the answer. Yes, the answer is physical implementation. And physical implementation is why topological qubits are mentioned in the project. Topological qubits are resistant to external factors and have properties which can be used to make qubits. Now, let's say that again. They are stable and we can make qubits out of them. Now, it doesn't take a 150 IQ move to put it together and say that they can be used to make qubits which are stable. That means resistant to external factors. And that is why topological qubits are interesting, and we can certainly say that in future of quantum computing, topological qubits play a very important role. And that wraps up the topological qubits module.